In this video, we will discuss about the phasor measurement unit data communication. So PMU data communication related information and the standard required for PMU data communication is defined in IEEE C37.118.2, which defines the following types of messages for PMU communication. So first one is data messages, which corresponds to the measurements made by PMU. Second is configuration messages, which contain the information about calibration factors and the metadata. What is metadata? Metadata is the data of data, means the information related to data being transmitted over the network. Now, metadata is required to properly decode the data messages, which are normally in the machine readable format. Now, what is packet? Packet consists of various layers of network protocols necessary for efficient and secure message exchange over the network. Command message is required to control the operation of synchrophasor measurement devices and the transmission of data configuration. A typical size of IEEE C37.118.2 data word is around 112 bytes. Now let's talk about the C37.118 data frame. So if you see on the left, it is a standard TCP/IP packet where the Ethernet header and Ethernet footer is on the top and bottom. So Ethernet corresponds to your physical as well as data link layer related informations. So we need Ethernet header as well as footer to indicate the start and stop of the frame and other activities. Then we have the IP address stored in the IP header. Then we have the UDP header for routing of the messages, and then after that we have the payload section to store the data. So this payload section will house the frame of IEEE C37.118. So this is your standard TCP/IP frame. Inside that, in the payload, we will house our C37.118 frame. Now, what are the various components of C37.118 frame? So first 2 bytes correspond to sync. Sync means it is required to provide frame type and version number. Then we have frame size to define what will be the size of the frame. Then ID code of 2 bytes, which defines the source identifier of incoming stream. Then we have SOC, that is called as second of century. This provides the information about the timestamp measurement, which is in UTC format, that is universal time coordinates. In UTC, what we do, we count number of seconds lapsed since 1st January 1970. So in SOC block, you will see a large 12-digit number which tells how many seconds have lapsed since 1st January 1970. Now the next block is fraction of second, which provide precision information related to timestamp because it stores the information related to fraction of second with accuracy up to 1 microsecond. So SOC and fracsec are the 2 blocks which do the time stamping of the data frame. Now after that you have the phasor data housed in the frame, and in the last you have the checksum bytes to determine any error in the transmitted word. Now in this data frame, what information you store. So first is the sync block, which is again to provide the frame type and version number details. Stat block is to provide information about the complete status of this data block. And then we have the various phasor data informations. So first block of the phasor may contain voltage phasor information. Second block may contain current phasor information. Then we have frequency information, rate of change of frequency information, and analog as well as digital information which you want to share along with the phasor data. So this is how the data frame of the phasor measurement unit is created and transmitted over the network. Now, how it communicates with the phasor data concentrator? So there happens the handshaking between PDC and PMU first. So PDC first send command frame which asks for configuration information from PMU. So PDC will send command frame to PMU. In return, PMU will send configuration frame to PDC, and then when it gets the command frame information, it will send again the command frame to turn on the transmission of data frame. After receiving the command from PDC about sending the data frame, PMU will start sending data frames. Now, as we saw in the previous slide, data frame sends data using UDP. Why UDP? Because in case of TCP, we need the acknowledgement to be coming from the receiving end, which delays the data transmission. So to increase the data transmission rate and making the data reporting rate very fast, instead of TCP, we utilize UDP for sending the data. Now, after a certain time, if PDC wants to stop PMU to send the data, PDC will send command frame again to turn off the data transmission. So this is how the data transmission happens between PDC and PMU. Now let's talk about the bandwidth requirement for data communication. If the data reporting rate is 10 frames per second, the number of bits per second required is 6720 bits per second. If we are reporting only 2 phasors in the frame, suppose if we are reporting 12 phasors in the frame, the bit requirement will increase to 9920 bits per second. Now, if data reporting rate increase to 25 frames, for 2 phasors, the requirement of data reporting is 16,800 bits per second, and for full frame, like having 12 phasors to be reported, we will have 24,800 bits per second. Now, if the data reporting rate is 50 frames per second, the bandwidth required increased to 33,600 bits per second if we are sending only 2 phasors, and 49,600 bits per second if we are sending 12 phasors per frame. Now you can understand that the data reporting rate increases when the number of frames per second to be sent from the PMU increases. Now if you have 50 frames per second of data reporting and we have 1 PMU, then it is close to 50 kbps, that is 50 kilobits per second. Now if we have say thousands of PMUs, let's take the example of India. Right now we are in the process of deploying 1700 PMUs at various buses. Then if we compute the data reporting requirement, you can simply check that if you multiply 50 by 1700, it will be close to 85,000 kbps of speed. That means 85 mbps speed is required for getting the data at the control center, which is monitoring all the PMUs. So 85 mbps requires strong communication channels which can handle this huge data transmission. Now another challenge is that you have data reporting at the rate of 85 mbps, and if you want to do the analysis, every second you are getting 85 MB data. Your application should be developed in such a way that it can process data very fast, so that before the next 85 MB data comes, your application will complete the process and give you the output. So there are challenges in the utilization of phasor measurement unit data because of its very fast data reporting rate. Now let's talk about the various applications of phasor measurement unit. First is the protection against fault. If we have PMUs connected at various buses, whenever we have fault, we can immediately see the response of PMU, and accordingly we can take action. Since the PMU data reporting rate is very fast, we can get the fault information at very fast pace and we can take actions accordingly. Stability monitoring. Since the angle information is given by PMUs at almost a real time, we can trace the angular variation of various buses, and immediately if we figure out any angular separation beyond a particular limit, we can take action to save the system from any stability issue. Then special protection system monitoring such as AGC, load shedding and high voltage DC transmission can also be done using phasor measurement unit data. We can also do the calibration of instrument transformer, because PMU data is considered to be most accurate data available for any analysis. Using that data, we can calibrate our instrument transformer. We can do the model validation. If we have developed any mathematical model, we can use the PMU data to fine-tune the model output, because we consider PMU data as most accurate data available. Fault identification. Using PMU data signature analysis, we can identify the fault in the system. Then energy market operations like real-time ATC calculation or congestion management can be done with the help of phasor measurement unit data. We can also run state estimation using PMU data. If we have PMUs connected at all the buses, the state estimation becomes linear state estimation, and the process of state estimation becomes very fast, and this makes sure that the state estimation completes before the arrival of next PMU data set. So in that way, the state estimation can be utilized for real-time monitoring and control of the power system network. Now, FACS devices monitoring. Flexible AC transmission system devices we can monitor and even fine-tune with the help of phasor measurement unit data. We can also utilize PMU for any emergency control for the power system network. We can use PMUs for wide area monitoring and control, because PMU helps in giving the data time stamped with the help of GPS clock. So we can better monitor the power system network over a wide geography, and the data sent by the remote PMU will be time stamped, and we time align the data and verify the state of the power system network. We also utilize the phasor measurement units for various controller tunings such as PSS, that is power system stabilizer. So those tuning can be performed with the help of PMU data. So these are the few applications which we can implement with the help of phasor measurement unit data. So in the next video, we will start our discussion on the smart meter.